Planar graph is such that each face has degree greater than or equal to 4. So we said that the degrees of each face was what? Greater than or equal to 4. That's what's given. All right. Now, if we multiply by the number of faces, it's just 4 times f. Does that make sense? So you have 10 faces or 5 faces. It's 4 times that. And then the total degrees look like this of all the faces. So from the given, they're saying that the degrees of each face is greater than or equal to 4. If you multiply by the number of faces, you get all of the degrees. Now, we had a way of looking at the sum of degrees of all the faces was equal to, it's like the sum of degrees of all the vertices, it's equal to what? 2e. Because think of a face having an entry and an exit point. That'll make one edge. So this will be 2e. And this is 4f. Once you get to this point, are you okay? E plus 2 equals v plus f. We did that before. So e plus 2 minus v is f. So 2e is greater than or equal to 4 times e plus 2 minus f. Oh my goodness, minus v. All right. So then you multiply through and you do a little bit of algebra. You get 2e is greater than or equal to 4e plus 8 minus 4v. And then I'm going to subtract 2e. And then I'm going to move these to the other side. So you'll get 4v minus 8 greater than or equal to 2e. Uh-oh, is this going to work? Divide by 2, and you get 2v minus 4. E is less than or equal to 2v minus 4. There you did it. You showed that. Is that good for 3? Who asked that one? Alex, are you good? What were you having the most trouble with? The first step?
I don't know how to start.
Yeah, and I think that's the hardest part. This is rewritten to be that. The degrees of each face, I is each face, is greater than or equal to 4, and then we just multiply by the number of faces to get all the degrees of the faces. This is our goal because we want to get that 2e. Next, I did 6 in class. All right, take a look at number 8 here. So 8 says, prove that in a simple connected planar graph, v is greater than or equal to 3. We're using this statement from before. There are at least one vertex of a degree less than or equal to 5. This is definitely an above and beyond, but it's going to make sense to you. We want to prove that at least one is less than or equal to 5. We're going to do a contradiction proof. What's the opposite of at least one less than or equal to 5? All of them greater than or equal to 6. Okay? So the way you would start this one is you would start by saying that all of them, all of the degrees are going to be greater than or equal to 6. And so you could do what we did just before. Each vertice, the degrees of each vertice is going to be greater than or equal to 6. Then I'm going to multiply by how many vertices that we have, just like we multiplied by how many faces there were. And that'll give me the sum of all of them, degrees of the vertices. And then what is the sum of the degrees of all the vertices the same as, again? 2e. 2e is greater than or equal to 6v. So e is greater than or equal to 3v. So then what I did is I said, we proved that e is greater than or equal to 3v. So the e's are out here, greater than or equal to 3v. Are you okay with that on a number line? But they said in the thing we developed before, e is less than or equal to 3v minus 6. If I solve for 3v, e plus 6 is less than or equal to 3v. So if e plus 6 is less than or equal to 3v and e is greater than that, does that make sense? Can you have something plus 6 being less than just something?
If b is negative. No.
V can't be negative, but good point. Interesting. That's what's nice about the, do you know what branch of math we're talking about now? Discrete math, whole numbers, and positive.
That's pretty good.
Yeah, no, I like it though. I'm glad you brought that up. So this is a contradiction. E plus 6 can't be less than e. So therefore, at least one vertex of degree is less than or equal to 5.